Hello and welcome. My name is Carrie Ann Taylor, and along with myself from Echometer, we have Gustavo Fernandez, who will be running the chat and assisting with Q&A. Also, Dieter Becker, Dr. Tony Podio, Ken Skinner, and Lynn Rowland. So today is our 11th session, which is really exciting. When we started these, we weren't sure what the response would be, but we felt the need to address some training concerns and just stay connected. Things have sure changed, and we really enjoy the interaction with you guys and seeing you and hearing from you. And we'll continue doing these sessions for as long as you want to hear from us. Today's session is on fluid level measurements in shut-in wells, and it's a continuation of the discussion on static bottom hole pressure calculations that we had from session 4, which was titled Shut-in Wells in Today's Environment. So if you haven't watched that session and you're looking for some additional information, then please feel free to go visit our Ask Echometer webpage and you can watch that session as well. That was session 4. So with that, Dieter, I will go ahead and turn it over to you to get us started.
All right, thanks, Carrie Ann. And as Carrie Ann mentioned, we're following up on a presentation we did earlier on static bottom hole pressures. And this presentation was put together by Tony Podio and Gustavo and myself, so we may all chime in here in the middle of this presentation. But on this one, we're changing up a little bit from the first one, and we're going to talk more about flowing type well, whereas in the first presentation it was on pumping wells. And we'll rehash a little bit of some of the things we talked about, and then we'll go over the differences between calculating a static on a flowing well or say a gas well and that of a pumping well. And Gustavo has a few examples that he'll walk us through looking at the presentation. But one of the things is we'll talk about coming up with a static bottom hole pressure or reservoir pressure and why that's relevant and why that will give us a better understanding of the producing well's performance. There's different ways to do this on different types of wells, and today we're concentrating on wells that would be calculated as a flowing well. So that would be, say, a flowing gas well. But also kind of under that same scenario would be a gas lift well, because you're still, in essence, flowing up the tubing, or even a plunger lift well. We covered some of the pumping type wells in a previous presentation. And injection wells are yet a different case for coming up with static bottom hole pressures. But we'll talk about some of the general procedures and considerations that you need to take into account to do these tests and to come up with the numbers. So in doing this on flowing wells, we'll talk about the fluid distribution and how that changes during the test. When we start out, we may have fluid all the way to the surface. If it's especially if we're producing a gas well above critical velocity. And as we shut in, we may see that liquid level fall back and change the distribution of the oil, water, and gas. We'll see how that's affected on gas lift wells in two different scenarios. One, whether you have a packer in a well, or one where the annulus is open. We'll also talk a little bit about static bottom hole pressures on plunger wells. Today's environment really makes it easier to come up with static bottom hole pressures. And I've always thought that static bottom hole pressures was a difficult number to come up with, because we'd rather have the money in the bank as opposed to the number. We'd rather have the production, and especially our managers. But these days we're shutting in wells anyway because of the current environment, and we may have a better opportunity to get the static bottom hole pressures or shoot fluid levels on shut-in wells. So that's an opportunity that we just don't want to miss today. We'd like to take advantage of that opportunity. So why do we need this static bottom hole pressure or reservoir information? Well, one, we need it to determine the well's performance. In the last presentation, we talked a little bit about inflow performance relationships, and we talked about those IPR calculations. We might just touch on those today. We're not going to go as in depth on the IPR calculations as we did in the past. But if you want additional information on that, feel free to contact us and we'll provide that. It'll give us a better idea of our production efficiency, help us size the equipment, determine in the case of a pumping well, what rate we would get if we'd pump off the well, but maybe on a flowing gas well, what rate we could get if we could deliquefy the well. In addition, we can determine depletion. We can see how the static bottom hole pressures are changing over time. And that's a good number to know. And if we do that on individual tests, individual wells, we'll see it. But if we do it on a variety of wells throughout the field, we may see that some parts of the field are more prone to depletion than the other parts of the field. And, you know, this will provide us data to calculate reserves. So what do we need to do to shut in, do a test on a shut-in well? Well, one thing we need is management approval. And in the past, that's often been a problem because, as I said, the management, perhaps their bonus was based on the profits or something like that, where they wouldn't want to shut in the well. Or they'd have to make payments to bank loans or something, and they needed the cash flow. So sometimes that management approval was hard to get. But in cases like today, maybe we don't have a market for our product. Maybe the well's shut in for other reasons, like a gas plant turnaround, or the storage facilities are at capacity. Maybe if you're offshore, maybe there's maintenance on the offshore facilities. Or if the well's even down for mechanical problems, that would be a good time to get a static bottom hole pressure. You know, I've often told people that if the well was down for a mechanical issue like a rod part, and it was going to be several days before they could get a pulling unit out there to fish the rods and repair the issue, that might be a good time to get a static bottom hole pressure. But there are differences between producing bottom hole pressures and shooting static liquid levels. And on a producing shot, we tend to have fluids flowing into and out of the wellbore. You know, we still have fluid coming into the perforations or in from the formation. We may still be producing it. We may momentarily close in a valve, but they tend to be noisier, especially if they have gas production. We tend to have gaseous liquid columns because we still have the gas flowing into the wellbore. It's percolating through that liquid column, and we have to do a correction for that. And on a pumped well, we tend to have oil in the annulus above the pump when we're in a steady state condition because of the gravity segregation. The oil's lighter and it'll float to the top of the annulus. In a flowing well, like a gas well, we'll have a mix of oil and water, but even that mix will change after we shut the well in for a static shot. So once the well's truly static out, there will be no more fluid flowing into or out of the wellbore. And in this presentation, you'll somewhat see a transition, a slide that shows the transition between a producing case and maybe a true static case. But once it's truly static out, we won't have any fluids flowing in. So it'll be quiet. We won't have a gaseous liquid column anymore because there will be no more gas coming into the well. It'll be a solid column of liquid. And in this case, we can have oil and water in the well, whether that's in the annulus or in the tubing. And we'll discuss a little bit about how that's calculated on a flowing well, if we're flowing up the tubing, and what our fluid distribution is going to be after we shut the well in. So if we have a chance to prepare for this shut-in, there's some steps we'd like to do. And we might not always have a chance to prepare for this, because perhaps it could be a mechanical problem that happens suddenly, but ideally we'll be able to prepare for this. And one is that we want to make sure our team's aware of what's going on. We don't want anybody coming behind us and putting this well back on production. We may want to lock out and tag out. We also may want to verify the condition of the wells, that as we shut this in, that we're not exceeding the pressure rating on any of our equipment, that we don't have any leaks or so on, that the well's in good mechanical condition. And we'd also like to get a good baseline production information, if that's possible, and a good producing liquid level, whether it's a pumped well or even a well flowing up the tubing. We'd still like to know where the liquid level was while we were producing. There's a few other things we need to keep in mind too. We may have some land and leasehold issues. For example, in the early 80s, when I was a young engineer, I essentially spent 2 years working as a production foreman. And I looked over a gas field during that time. And our gas market was severely curtailed at that time. There was a gas bubble. There was more gas than was needed, and we could not sell our gas. But the lease we were on required that the lease be produced at least once every 30 days to hold the lease. The lease was held by production. So the pipeline company would shut us in and not allow us to produce gas, but they were required to let us produce the wells in 1 day a month, so we wouldn't lose the lease. So if you're shut in for an extended period, especially on these flowing wells and gas wells, you may have to do some visiting with the pipeline companies to make sure that you're going to be able to produce the well enough, and that you're not just shut in and can't sell any gas at all. Also, long-term shut-ins may affect the performance of the well. We may have some wellbore damage. It could be that we have some corrosion going on if we have this well shut in for a long period of time and we're not using the proper corrosion inhibitors. It may be that we have some fill, perhaps from frac sand, and especially since we're not producing the well, that fill may be accumulating at the bottom of the well. We could have some issues with reservoir damage. One thing that can happen on a well that's shut in for an extended period of time is that you may have cross flow. If you have several zones open and you're normally producing where you're producing bottom hole pressure is low, both of the zones will be flowing into the wellbore. But as you shut the well in and the bottom hole pressure increases and one zone's pressured higher than the other, the higher the pressure in the wellbore may increase towards the pressure of the higher zone, and it flows into the lower pressure zone. And that cross flow may contaminate the other zone, bring in some incompatible fluids, cause some formation damage, and so on. The thing I'd like to do, whether with any shut in, if I know ahead of time, besides shooting the liquid level, is just some other tests. If we talked about pump wells last time, but I often like to get a baseline dynamometer to see what it was like before we shut it in, so we could tell if any problems occurred. But perhaps on a plunger well, it would be good to do a plunger tracking test and analysis before you shut in a plunger well. Perhaps you had some scale forming or corrosion during an extended shut-in that might affect the plunger movement. So it would be nice to have a baseline before you shut the well in. Now, if we have time and the equipment, we can also do additional testing while the well is shut in. We can do a pressure transient test where we collect data over a period of time. We take multiple shots and we monitor the change in pressure over time. And that's a pressure transient test, and we can get additional information such as permeabilities, formation damage, and so on. And we'll have another session in the future to go into more detail on things like pressure transient testing. But let's talk a little bit about the flowing wells and what happens when we shut in a flowing well or a gas well. Well, we have gas and liquid redistribution. So we'll talk about different scenarios where we're producing above critical velocity, that's where we're making enough gas to carry the liquid to the surface. So in essence, we have a mist all the way to the surface. And we may not see a true liquid level in that case, but when we shut in the well, the liquid level falls. Another scenario is where we have liquid in the well where we're liquid loaded. Our gas isn't being produced at a rate fast enough to carry the liquid out of the well. So we'll have liquid in the well bore, but even in that scenario, as we build up surface pressure on the well, it may push that liquid back into the perforations. And we're going to talk about what happens when that goes on, what liquids go back in first, and so on. So as we do that, the bottom hole pressure will increase and also the surface pressure will increase. And as those pressures increase, the flow into the well bore, the flow at the perforations will decrease and eventually stop. And then the pressure not only in the well bore increases, but it'll increase in the reservoir between the well bore and the boundary of our drainage area, between the well bore and the drainage grate. Now the oil and water, when we're flowing, especially when we're in a above critical velocity, they're going to be mixed in the tubing because they're being carried out. But during the shut-in period, our water is generally heavier, so it will separate and fall to the bottom, and our oil or condensate will be at the top of the liquid column. So if they're separating like that, and our surface pressure increasing and going to push a fluid back into the formation, what's the first fluid that's going to be pushed in? Well, it's the water, right? Because the water is at the bottom of the column. So you'll see we'll have to monitor that liquid level and see what we have left and use that to calculate our how much oil and how much water we have in the well. Now, once the shut-in's complete and we're ready to turn this back onto production, one, we have to verify that our production facilities are ready and they're in a condition to handle the increased production. We've been shut in for a while. The pressure in our well bore is going to be greater than our normal operating conditions. So when we bring it on initially, it may come on at a higher rate than we're used to that well producing, and we need to make sure that our production facilities can handle that additional rate. Or we may need to choke the well back. We need to monitor that to make sure we don't overload our production facility. Now, since our well's been shut in, this also gives us an opportunity to do a drawdown test. And that's another type of pressure transient test where we bring the well back on production and we watch the pressure draw down and lower as the well's being produced. And it also gives us a chance to monitor the unloading of fluids, especially if we're in say a gas lift well. We might want to monitor what valves we're operating through and so on. When we bring this well online, we might also consider the need for additional equipment. You know, as we mentioned, and we'll see in some future slides here, that as the pressure builds up, it's fairly common on a gas well or a flowing type well where we build up a lot of pressure on the surface that it pushes the fluid back into the formation. And I would say that's the most common scenario that we have. But if we have a weak flowing well, one that has a low gas oil ratio that makes maybe or a gas liquid ratio that makes a lot of liquid and maybe barely enough gas to keep that well flowing, we may have to do something different to get that well to flow again. We may have to bring in a swabbing unit. Now that's unusual, but it does happen, especially if you're working in older depleted gas fields that accumulate liquid in the bottom. We may consider a separator, something like that. Soap sticks won't really help when the well's shut in because you don't have the flow to create the foam, the bubbles with the soap stick, but perhaps once it's going again, that may help unload some of the liquids that have accumulated in the well. But we're really after getting our static bottom hole pressure. And why do we want that static bottom hole pressure? Well, we mentioned the inflow performance relationship. And from our producing shots, the shots we take while the well's producing, we calculate this pressure in the bottom of the well bore while it's producing. When we shut the well in, the pressure in the well bore will build up and it'll approach the reservoir pressure. And we call that the static bottom hole pressure. Well, if we compare the static bottom hole pressure to the reservoir pressure, we can get an idea of what percentage of the maximum production rate we're getting out of the well. Are we getting half of the production that the well's capable of giving up? Are we getting all of it? That's what we get from the static bottom hole pressure gives us the ability to perform those calculations, and we can do our inflow performance analysis as we talked about in the last presentation. So once we shut the well in, what happens with our fluid distribution in the wellbore? Well, when we start out, our fluid may be near the surface. It may be all the way to the surface, especially if we're above critical velocity and we're carrying the liquid out of the hole. If we're liquid loaded, we may have a liquid level in the tubing if we're flowing up the tubing. But once we stop our flow, this liquid column here might be a mist. It might just be 20% liquid, and we're going to see this liquid level fall back. And we're going to see the surface pressure increase, and we're going to see the gas that's in this gaseous liquid column percolate to the surface. And as that casing pressure increases, we may actually be pushing that liquid back into the formation. And that's, from my experience, is a fairly common thing where the increase in surface pressure will push that fluid back down into the formation. Now, as this liquid falls back, we'll also tend to see the oil and the water in mix separate. As we're flowing and we're above critical velocity, this will be oil and water mixed all the way to the surface. And we'll start seeing a boundary between the oil and the water layer, with the water being at the bottom because it's heavier. And if fluid is pushed back into the perforations, the first fluid that's pushed back will be the water that's being pushed back. If we're not producing above critical velocity, if the well's liquid loaded or there's a liquid level in the tubing while we're producing, then we probably have a natural separation already of our oil and water in the tubing. So the static bottom hole pressure, which is just, we tend to use it as another word for the reservoir pressure, that's the pressure out at the edge of the drainage radius. That's as far as we're reaching out into the reservoir to drain. And it's the pressure out there, and that's the pressure that's available to push the fluids in the wellbore, as we saw on this slide over here. So most of the time, we mentioned we're eager to produce our wells, and we don't often have the opportunity to come up with a static bottom hole pressure. So it's generally guessed. Maybe they did some pressure surveys when they first completed the well. Maybe we're figuring on an average pressure gradient in the area. but we generally guess at it and would really like to have the number, either measure it or calculate it. And in order to do our inflow performance relationships, we'd probably like to have that number within 15% of the actual number. And that's to calculate the potential in the wellbore. But if we want to do it for reserves, we want a much more accurate number. So we're going to measure a static bottom hole pressure, a static liquid level, excuse me, and a surface pressure in well. And then we'll use either the TWM or TAM software. Or for those of you that are still using the script chart recorders, we have the AWP 2000 program available. So we mentioned the different scenarios where we're above and below critical rates. If we're producing the wells above the critical rate, the gas is flowing fast enough to carry the liquid out of the wellbore. It's carried out by that gas flow. And when we shoot a liquid level, we might not see a liquid level at all because it's a mist in the wellbore. The liquid level is essentially at the surface. And once we shut the well in, we'll see a liquid level form as it starts dropping back down and the liquid's no longer carried out of the wellbore. But on a liquid loaded well where we're producing below the critical rate, we have gas flow at the wellhead, but it's not enough to carry that liquid out of the wellbore. So in this case, we have a liquid level that we can see, and we should be able to see it on our first well. We'll also see that collapse as we shut the well in. You know, it will no longer be a gaseous column. It may get pushed back into the formation. Just on a side note, we generally don't like liquid loading wells because that liquid loading is holding back production. You know, it's increases the producing bottom hole pressure. So we'll take steps generally, or try to take steps to eliminate that liquid out of the well, whether it's plunger lifts, soap sticks, or other things. So when we shoot the liquid level on a gas well, we generally attach to the tubing, especially if the well has a packer on, you know, and if there's a packer, the tubing's generally the only way we can see the static bottom hole pressure. And in this scenario, in this slide, you see several different pictures. We see a wired remote fire gun. A wireless one would work just as well. We see a compact gas gun. The compact gas gun's an excellent gun. Maybe not as convenient because it's not remote fire, but it has the ability to explode and implode, and it generates a real crisp shot. It's a good gun. And then we have a 5,000 PSI gun for wells that have higher pressures, and even a 15,000 PSI. And these all show the guns hooked up to the tubing in different configurations, whether it's on a lubricator or going directly into the crown valve or swab valve. If you didn't have a packer in the well, you could also shoot down the annulus. And there are some benefits to shooting down the annulus if you're flowing up the tubing, because it tends to be a quieter shot, and you have tubing collars to count and so on. So on our gas well, again, we've been mentioning the above and below critical velocity several times, but this slide just illustrates the one that's below critical velocity, where there's a liquid level in the well while we're producing. We don't necessarily like that because this liquid holds back production. If we were above critical velocity, that liquid level would truly be at the surface. So here's a scenario of fluid levels over time when we shut in the tubing. And this was a liquid loaded well. The liquid level was quite high. So maybe if it made a little bit more gas, it might have been above critical velocity, but it was liquid loaded with a substantial amount of liquid in the well. And you thought, well, maybe that liquid level is somewhat questionable. It's not real clear. But as we shut the well in, we see that kick starting to drop and move. And again, that reinforces the concept that that's the liquid level. And as we build up pressure on the surface, our sound's traveling better, and the liquid level's still dropping, but the liquid level becomes more clear. So if you're doing a static shot or even a pressure transient test, I often find out that the farther you are into the test, the better the quality of your shots become, because your pressure on the well increases, and the higher the pressure, the greater the density of the gas in the well, the greater the ability of the sound or the acoustic pulse to travel through that gas. So on this well, we saw the traces here, and over on the right-hand side, you can see how that liquid level was falling with time when this well was shut in. So this is a good time for questions. I haven't been monitoring the chat. I think Gustavo's been out there, and he might see if any questions popped up there.
Here we have a question from Lupe. She's asking, a rod pump well that has been shut in for quite some time, it is better to bleed the gas off a day or two before starting pumping unit to get the casing PSI down to allow the fluid come back into the wellbore?
Tony and Gustavo, or y'all might jump in and put in your thoughts on that. And I think it depends on the well, but I think if you had a well with a high casing pressure and that casing pressure pushed the fluid back into the formation, that might be an acceptable practice. Again, when you open up the casing, you're probably going to have a higher gas flow than when you normally produce the well. And we got to make sure that we're not overloading our equipment at our facilities, you know, that we're not bringing the gas into the separator too fast and things like that. So there may be a reason you want to open up the casing a little bit earlier, and you may want to choke the casing back again, like I said, not to bring the fluid in so fast. But once you have the casing pressure off of it, the fluid will start flowing into the wellbore. So that might be something you could do on a short-term basis, you know, 15, 30 minutes. Maybe you have a well where it'll take a longer period of time. So I would think the answer would depend on the well that you have, the exact answer.
Well, thank you, and that's the only question we have so far.
Okay. Gustavo, I'm going to stop sharing my screen so you can jump in there with some examples of static bottom hole pressures on flowing wells.
Okay. You can see my screen, and what I'm going to be showing is a series of wells which I have under my group of wells for today's sessions. And the first well that I'm going to show is a gas well that was flowing above the critical rate. And this well had a series of shots. We started to taking the fluid levels just a minute after shutting the well. And here's a small preview about what we'll be having on this review of the well. So the first shot was shot at 1 minute later after the shut in, and then consecutive shots 6 minutes, 11, 20, 25, and so on. And in this preview, we can see how the liquid level on the first shot, we want to be reviewing that in a better way. This is the first liquid level shot just 1 minute after shut in. The first shot was taken 1 minute after, and then 6 minutes, 11, 20, and so on after shutting the well. And we can see on the first shot, and we will review this better, there is not an obvious kick from the liquid level. Actually, there is no liquid level kick. After 5 minutes, we continue shooting the well, and there is a kind of obvious down kick from the liquid level. And we can see how the time to the liquid level increases shot after shot, and is coming even more clear after every shot. And this first shot on the well, I'm trying to show the full trace. There is not an obvious kick from the liquid level. If we go to the next shot, 5 minutes after, we can see a clear down kick from the liquid level, and that's only 2.2 seconds. And the time to the liquid level was 1562. And we can see on the next shots, the liquid level key continues appearing, but it's moving down shot after shot. And probably this preview illustrates that very well. Something important, that the purpose of this kind of test is different than liquid or pumped wells. Let's say we are right now trying to calculate the producing borehole pressure. And the way we will do that is with multiple fluid level shots and not with a single shot as usually is done in a rod pump, a PCP, or an ESP well. And in this type of wells, the technique is quite different, as you will use multiple fluid level shots, and you will take some part of the information to calculate or estimate the producing borehole pressure. How we will do that is, well, we will take a representative number of shots, and from the liquid level report, we're going to focus, let's wait for the report. We're going to focus not on the producing borehole pressure, that would be unrealistic, but we're going to see the pressure at the gas liquids interface, which is the pressure right on top of the liquid level. As soon as we can start seeing the liquid level, we can check out the fluid level. The first shot is not clear, but the second shot is right there. If we keep moving in time, so the liquid level is moving down, and each of those shots has a calculation of the pressure on the top of the liquid level. So after we analyze all the shots, checking how to monitoring the liquid level falling in the well as the tubing pressure is building up, and we can see how the pressure is building up on every shot, and the gas liquid interface pressure is being accounted. We can use the TAM software to export the data, and this might be a topic for a different session, where you can do a data export from the software, and you can use some templates to export the desired set of data from a specific group of wells. And I've already done that for you, and I had all that information in a spreadsheet. So what I've done is taken the desired information for all the shots in this particular well, and part of the data that was exported is the time to the liquid level, and I made the calculations so we can see the difference of since we started the shot in the well. After 45 minutes, this test was conducted. As a result, we have a top to the liquid level. The first one is not visible, but we can also have some data that we're going to plot. So we're going to focus on two things: how deep is the liquid level, and from that value, we can calculate how much fluid we have above the perforation or the desired point where we can want to calculate the borehole pressure. And we can also consider the pressure at the top of the liquid level, at the gas liquid interface. So by having that information, we have here some points, and we can plot and estimate it or calculate the producing borehole pressure. And this well, using the previous shots, was 3,653 psi, about that. And again, this is a simple technique. You can extend the test, and usually gas wells with high gas flow rate, sometimes even in half an hour, the well can build up the pressure high enough to be very close to the static pressure. Sometimes take some hours, as the example shown. Sometimes take a few hours, 12 hours to reach the static pressure, but will depend a lot on each well. So after having this many shots, and you want to be sure that you're selecting the liquid level properly, and when you have that, usually from 2 shots, you don't have colors to count. And then we're using a different method. We're using an acoustic velocity calculation. Let's see if I can make this out. So we're using the gas gravity for this well in order to calculate the acoustic velocity for each shot, and as a consequence, the distance to the liquid level. So that's how you usually use the Echometer equipment to estimate the producing bottle pressure when you shut in the well. So the next well I have is actually a shutting well for a long period of time, and we're going to focus on the first shot. Usually, when you have a high pressure well in a gas flow well, you have this condition. What we can see is that there is no liquid level kicks, and I'm going to focus on these kicks at the end of the well. When I try to highlight that information, we see a huge up kick and then some down kicks. I am going also to show you the full trace where we have enough recording time, and we see a series of kicks. So this is the first up kick, then it comes to a down kick and an up kick, and that's all we are having the end of the tubing exposed above the liquid level. So by shooting the liquid level, usually it's really easy or simple to interpret, as we have a very good downhole marker from the end of tubing for these tubing shots, and then the selection for the liquid level. Once we have that, the software, we can use the software and determine the liquid level based on the downhole marker. That would be probably the best option to take. And on the report, we will try to view some of the information. So this well obviously doesn't have any more liquid in the tubing, and we at this point we don't really know at the producing state if it was holding liquid or not, but we are going to say this well is producing above the critical rate. And on the static fluid level report, we have two conditions. We have a condition from the production shot and the static shot report itself. I'm going to check the worksheet for the static bottle pressure, and if the well was producing above the critical rate, and as we saw in the previous example, the liquid level was on surface, or there was not liquid holding, so we can tell the software that we had a liquid level at 1 feet, as the software right now do not accept the 0 distance to the liquid level, so we will just say 1 feet from surface to the liquid level. So we kind of represent this a full well and a very low liquid percentage, as a high gas velocity is able to carry all the liquid out of the well. So on this one, we will keep it with 20% liquid, and this is just the production rate that the well had on the producing state. So by doing that, the software will be able to calculate the pressure profile. And on this well, we had a case, or in this case, a tubing pressure, and there is no liquid in the tubing, so we have a linear gas gradient down to the formation depth, which is 10,630 feet. And all this is calculated to TVD. This is a vertical well. Our next example will be a deviated one. And the software will make a pretty good calculation of the static bottle pressure. And this is a good condition. There is it's a pretty accurate calculation again. The next well that we can review will be another static well, and it's about the same configuration. It's a much deeper well. The formation is, or the fluid level is over 15,000 feet. Same configuration, up kick from the end of tubing, a down kick for as a repeat exactly at the same time. And we're going to focus on the report, and we'll see the software is considering the formation depth and it's calculating the true vertical depth. For 1 minute, I'm going to just show here, this is a deviated well. The end of tubing is at 15,500 feet, but the formation is 15,602. That's the point where the pressure is being calculated. Then the software, we will use the survey information to estimate the true vertical depth of the formation. And that results in 14,810 feet as a true vertical depth. Following the same principle, we have a clear downhole marker. That's the app kick from the end of tubing. We will use that information and tell the software to use that app kick. And for the people who's not used to work with TAM, you can go to the downhole marker option and adjust the marker selector and just place it on the app kick that you have for the end of tubing. That will come with an acoustic velocity calculation, and the software will have a distance to the liquid level much more accurate. With that information again, we can check the static report and check on the static bottle pressure worksheet, and we'll assume the same. The well was flowing above the critical rate. The well was full of liquid, and right now, due to the high gas pressure, all the liquid present in the well was pushed back to the formation. Being that the case, the downhole pressure calculation was 2,500 above that at the formation depth. We can monitor how the pressure behaves, and there's actually not much build up on this well, so we can consider this as a representative static bottle pressure. Probably the most uncommon thing here is to realize that static condition for gas wells or high gas flow rates wells is quite different than an oil producer well, where in the static condition you can see how the liquid level actually rises compared to the production state. And in this case, for the high gas pressure and rate, the liquid level is pushed down back to the formation on the static condition. That's our kind of the three examples that you might be facing. That's really common to see empty wells or no liquid columns in a gas well. And ready for if you have any question. Dieter, you want to start sharing your screen?
Thanks, Gustavo. So when we talked about this, we were mostly doing single shots. We'd go out there and even in some of Gustavo's examples, he'd go out and do a single shot for a static. His first example, he showed how he was shooting several liquid levels in the producing case to watch a change in the fluid level. And that's okay just to go out there and shoot one liquid level when it's static down. But one of our criteria for determining if it's static out is when things stop changing. So maybe we know in an area that it takes 3 days or 5 days for a well to reach static bottom hole pressure. But if we don't know, we're going to want to measure several fluid levels and track it. And when they stop changing, we know we're at the static or approaching the static. And if the well is a distance from us, that might be a problem to have to travel out to the well and shoot liquid levels on a regular interval. So we're going to introduce just on a few slides here, just mentioning a new product that's coming out. We have several of these in the field, but it's called a RAM. It's a remote asset monitor. And it's just a little box that we put our wireless space station in. And it can control the acquisition while we're not there. It can schedule fluid level shots. It can also do the same with dynamometers. We'll look more here at some examples from the fluid levels. But we're just introducing this here. In the future, we'll probably have a Echometer session on the RAM. But it's this little box. It's talking to all the sensors on the well, in this case, the gun. Here's a pressure transducer on the well, the dynamometer sensor. And it even has the ability to control a motor valve. We're using a Kimray valve to close in the flow line. So you can open and close valves with it. You have remote control for that. So in our common scenario, when we use the wireless equipment, we plug the base station into our laptop. And that base station communicates with the different sensors. Well, if we'd like to collect data automatically over an extended period of time, we'd like to leave something there other than a laptop. You know, a laptop uses a lot of power. This time of year, it tends to overheat and so on, that we developed this RAM. And it takes the place of a laptop. There's a computer inside the RAM. The base station sits in there. So it's a small container. It's battery operated. It works with the wireless equipment. And you can set it up to acquire the data while it's unattended, set up a schedule of tests. And we're going to see we can connect this to the cloud, or you can talk to that RAM directly with a laptop. So you can go out there with your laptop, use the laptop to program the RAM to collect fluid levels on a specific interval, and then disconnect your Wi-Fi connection to the RAM, come back a day or two or even a week later and harvest the data, collect all the data that the RAM acquired during that past week. But it's also possible to connect that to the cloud. So in the next version of TAM, we're going to see different capabilities. And before we'd connect our laptop directly to the base station to talk to our wireless sensor. Now we can connect our laptop directly to the RAM, and then that's connected to the base station, and we can do that to set it up. Or we can even add one more layer in between, and that's the cloud. So we can put a cellular modem in the RAM, or even if the RAM if you have Wi-Fi or internet access in the field, it can access that. But most common is putting a cellular modem in, so that we have a cloud server that we can connect to from our laptop, and then that cloud server will talk to your RAM wherever it is, and you can either do a manual fluid level shot because you're connected all the way to the base station, or you can program the RAM to shoot a fluid level at whatever interval it is, and then you can connect to the cloud a few hours or a day or so later and collect all the data that's been acquired during the last day or so without having to drive out to the well. So it makes it much more convenient for getting static liquid levels. And here's an example. This was on a pumping well, but you can see where it was acquiring the liquid levels while the well was pumping, and we saw the normal producing liquid level. And then the well was shut in, and we saw the liquid level rise. And then the well was put back in production, and we saw the liquid levels draw down again. And you can do all of this without ever having to drive out to the well once you have the equipment on this. So this is a useful tool. We'll talk more about it in the future, but we just wanted to introduce the concept because it is quite handy for using on static liquid levels or continuous monitoring even of production well.
Okay, that's fine.
But let's look at about 10 more slides here on just shooting static liquid levels on gas wells. And right now we're going to talk about a gas lift well where we have a packer in the well, where we have a sealed annulus, a packed annulus. And in essence, the flow up the tubing will act just like a flowing gas well, but we're just injecting gas into the well to help unload the well. So what we might want to do before we shut this well in is we may want to take some fluid level measurements while we're injecting. And we might want to take a fluid level shot down the annulus. And that way we'll see what valve that we're operating out of our gas lift system. And we may also want to take a liquid level shot down the tubing. Now, if our gas lift system is operating properly, that liquid level should be at the surface. But if perhaps we got gas going in a valve that's up above the liquid level, we may be cycling some gas. We may not have enough gas in there to lift the liquid to the surface. We may, in essence, have what would be like a liquid-loaded gas well. So if we shoot one down the tubing, that would just be a good quality control check. Ideally, again, it should be at the surface, but it might help us identify problems. So once it's shut in, we may want to shoot periodic liquid levels down the tubing until our change in the surface pressure and the fluid level slow down, until that fluid level stabilizes. And we could do that just by driving out to the well every day and shooting a liquid level. Again, this might be a good application for the RAM. And then at the end of the test, we'd like to shoot a liquid level down the annulus again, just to maybe give us some ideas on wellbore integrity. See if we have a leak, if we have the liquid level in the annulus coming up or anything. Then once we open the injection to the well and we start unloading it, we can monitor that unloading. We can shoot down the tubing at periodic intervals and monitor it to see that the liquid's going to reach the surface and that it truly is reaching the surface, and then unload it. And here's an example of a fluid level measurement down the tubing of a gas lift well after it was shut in. And on the bottom trace, you see that it was taken at 9:53. That's the clock time. And a little bit later, not much later, but it was taken again, you see the liquid level falling down into the tubing, and eventually your liquid being mostly pushed back into the formation. And here at 10:44, the liquid level is at the bottom of the tubing and very little liquid in the well. But what if we didn't have a packer in the well, if we had an open annulus? We'd still like to shoot a liquid level down the annulus while we're producing the well to see what valve we're operating through. And again, we'd like to shoot a liquid level down the tubing or confirm some other way that the liquid level's at the surface. But ideally, the liquid level should be at the surface. If it isn't, we have a problem. But we'd like to identify that. And then when we shut this in, we'll shoot periodic liquid levels down the tubing as the liquid level collapses, and until our change in surface pressure stabilizes and decreases and the fluid level stabilizes. Also, since we don't have a packer, the annulus is going to be open to the formation, and that gives us yet another way to get the bottom hole pressure. You know, we have some advantages of shooting down an open annulus because we can use the gas lift valves may make a better marker down the annulus. We can count collars if we need to or whatever. But we would like to at least shoot down the annulus at the end of the test to see where our fluid level is, to see what gas lift valve we'll be operating through. And we can monitor the unloading then by shooting down a liquid level and seeing as we change through operating through different valves. Well, what about plunger lift wells? Well, if we do a static on a plunger lift well, I think a good practice is to catch the plunger in the lubricator. Because if we're shut in for an extended period of time, we don't want that plunger to get stuck in the wellbore. So if we're going to shut in for a while, we may want to catch a plunger up there, and then we'll shut in our casing pressure, our casing injection. If we have any, you know, maybe we have a GAPO well where we have some a gas assist plunger lift where we might be injecting down the casing. So if that's going on, we surely want to close that off, and then we want to shut in all our valves to the flow line, whether it's a tubing. And then we'll make periodic fluid level measurements down the tubing as the liquid level accumulates at the bottom of the tubing until the buildup rate stabilizes and our fluid level stabilizes. And then at the end of the test, we'll drop our plunger and monitor the plunger fall to the bottom. And we'll open the tubing to the flow line. And we'd like to use our plunger lift software to monitor one complete plunger cycle. So oftentimes, if you know you're going to be shut down for an extended period of time, again, it might be good to do a baseline monitoring of the plunger cycle before you shut the well in. Um, so here's an example of people that didn't have the plunger tracking software, but they would monitor their fluid level shoot fluid levels and monitor where the plunger was during the plunger fall. So they used a compact gas gun. They just shot down the tubing, and the plunger is the reflection off the plunger is gonna look like a liquid level, and you'll see where the plunger is at any point in time. So one of my first experiences with a plunger in a relatively low-tech area was on the east coast of the U.S. before the Marcellus field became popular there. And the well tenders there would catch the plunger and shut in the well for 4 days. And then when they put it back on, they would monitor the plunger fall by shooting with a strip chart recorder and a Model D to see when the plunger was on bottom. And then they would return the well back to the production. These days, we have the plungerless software. Lynn's talked about that. We can automatically track that. I don't have any slides on the plunger cycle, but again, we can monitor the plunger cycle on the plungerless wells. And the static bottom hole pressure is an important piece of the puzzle when we're trying to optimize our wells. And it's often a difficult number to come up with, but the current environment where we have more wells shut in, it's a good time to try and get that number. So we ought to take advantage of that number. With that, let's see if there's any other questions at this point in time.
Yes, I have a question here related to the RAM system, and they're asking if the RAM system right now is unable to perform extended pressure transient tests.
Okay, we have a few customers now using the RAM for pressure transient test. We also have one customer that's had it on a well for an extended period of time. We have one RAM that's on a well that's been running nonstop since the beginning of March, since the first week in March. And it's been collecting liquid levels that whole time. And that system is equipped with a solar panel. So that keeps the battery charged and keeps it operating. So it's relatively maintenance free. Other people are running shorter term buildup tests. We have one of our customer has run several pressure transient tests using the RAM, several tests about 10 days long. And in programming the RAM, we have several different options for the schedule. And one is a linear schedule, a shot every so many minutes or so many hours. But we also have the option to take the data on log cycles. And those of you that have used TWM for the pressure transient part of it might recall that you can take the schedule on a log cycle where you get more shots in the beginning when it's changing faster, and then it generally spreads out the shots towards the end of the test. And our default on that is 30 shots per log cycle, where it tries to take 30 shots in the first hour, will then spread out 30 shots between 10 and 100 hours, and then 30 shots between 10 and 100 hours, and so on. Now in TAM, we don't have the pressure transient analysis in there yet, but the people that are using the RAM for doing pressure transient acquisition are using another package for the analysis. We have the pressure transient analysis on our schedule to put on TAM, but we have a long list of software features to add on TAM. So that's we'll probably begin to work on that later this year on the pressure transient analysis. But right now we can collect the data.
Well, to complement that answer, Founder was asking this question. So bottom line, we have an equipment that can actually perform the shots in the schedule that we prefer, and even a log cycle, which is usually preferred to run the pressure transient analysis. We just don't have the pressure transient calculations in the TAM software yet, but the software can perform the fluid level shots, and using a different package, you can run the pressure transient analysis.
And that's correct. So,
Okay.
um,
Yeah, Samantha is asking if the run equipment can work under different climate conditions, like really hot climate, rain, cold, and so on.
yes, and that's one of the reasons we developed the RAM. And let me see if I can bring up a different picture of share a different screen. This is a RAM box, and you see this is on a well that was running since last March. But the RAM is actually in here. We have a battery in the bottom box, and the solar panel keeping the battery running. But there are several reasons why the RAM was developed, and one of them was the environmental conditions. When we first started doing the pressure transient test with the well analyzer, the laptops were a lot slower. And that was actually a good thing for pressure transient tests. As the RAM got faster, as the laptops got faster, as the laptops got faster, they generated more heat. And when they generated more heat, the laptops would often overheat and shut down. And that was a problem. So inside the RAM is a battery, but that battery is, there's a battery. I'm getting ahead of myself, excuse me. There's a computer that controls it, but that computer is rated to 85 degrees C. That's 185 degrees F. And that was one of the primary reasons that we came up with the RAM, was that it would work in environmental conditions where we're having problems keeping a laptop running right now.
Well, I would like to add another comment on thinking on the first well that we presented today, and that producing fluid level calculation, producing bottle pressure calculation based on multiple shots on the shutting well. A common problem that some user has been going through is by not understanding really well how to perform the test, they have been shutting the well and waiting for a couple of hours, and they come back and visit. And they say that because whenever they shoot with the well producing, they can't see anything. If they shut in the well and shoot the fluid level, they can't see anything. And the only way they can see a fluid level is if they wait. But the problem is they are actually shutting the well, leaving the well, and coming back in a few hours later. And that's what we saw one of the slides. In half an hour, the fluid level may drop 4,000 feet. So whenever they come back, the pressure they are actually measuring is much more a static bottle pressure than an actual producing bottle pressure. That was just a comment I wanted to add.
Thanks, Gustavo. But we see a lot of potential for the RAM in the future. It's going to be a product that'll help in situations like this, in pressure transient testing, and even in long-term monitoring of wells. You know, it's we see when we get out of the other side of this slow period in the petroleum industry, that there may be a manpower shortage, and that might make the RAM more and more important. But if there aren't any more questions, we got just a few more slides here, 4 or 5 more slides, and we'll talk a little bit about the calculation of the static bottom hole pressure from the fluid level. And this slide here is showing the fluid distribution in the annulus, but on a pump well. But it would be the same thing in the tubing of a flowing well, or a pseudo-flowing well, like a gas lift or plunger lift well. And we have different components going into that bottom hole pressure. We'd have the surface pressure, the gas column pressure, and the oil column pressure, and the water column or brine column pressure. And as the well gets shut in, we talked about the segregation of these fluids. And with the brine or the water being the heaviest, it's going to be on the bottom. And we mentioned that the fluids are sometimes pushed back into the formation, Well, since the water's on the bottom, it's the first fluid that's going to be pushed in. One thing we don't know that's an unknown to us is the oil-water ratio while the well's shut in. What's the inflow of the oil-water ratio? And the best assumption that we can make is that it's the same as the producing oil-water ratio. And that may or may not be true. You know, if one zone's a higher pressure than the other, the proportion of fluids coming from different zones will change. But that's our best assumption we can do. And TAM, as Gustavo used, will calculate how much fluid is in the wellbore at the end of the test. And if you noticed some of those tests that he looked at, you would have thought there was more water in there when the liquid level got pushed down, but there was a higher proportion of oil because the water got pushed into the formation first. In summary, the fluid levels that we get on shut-in wells combined with the producing fluid levels give us a lot more information about the producing efficiency of flowing an artificial lift well. We can do a better job of predicting the maximum production available from that well. The longer the well shut in, the better our estimate of the reservoir pressure will be. And this comes into play especially in the tight wells that we have today, the unconventional, the shales. They're very low permeability. It's measured in the nanodarcies, and they are very slow on building up. My experience has been mostly in the Permian Basin. When I first started out there in the early 80s, people said a 72-hour buildup was sufficient. I don't think that's sufficient. I would say, in general, the older conventional wells out there, maybe 5 to 7 days would be what you'd want to run. We'd like to get periodic fluid levels to see that we are truly staticking out and we're stabilizing. And, you know, programmable instruments like the RAM make that a little bit easier. In the future, we're going to talk about pressure transient testing. And even if we don't get to the point where we're truly stabilized out, where it's reached the maximum pressure that it's ever going to reach, the static bottom hole pressure, as long as we reach, say, a pseudo radial flow infinite acting portion of that buildup, and I know that's a mouthful, and we're going to simplify that when we talk about pressure transient testing, we can extrapolate what that pressure will build up to, a number called a P star, an extrapolated reservoir pressure. So we'll have other ways of coming up with an accurate reservoir pressure we're going to talk about in the future. But that summarizes what we wanted to present to you today. We really wanted to illustrate that the concept of doing static bottom hole pressures on flowing wells was different than doing static bottom hole pressures on producing wells. And show you some of those differences. We didn't go into everything in much detail as we did on the producing because we covered it back then, things like the IPR. But feel free to reach out to us and we'd be glad to help with any questions you have in the future or address any present questions you might have at this point in time. Gustavo, are there any questions?
We have a couple of questions only. One is time related. Samantha is asking, when do we think it will be ready for the market?
The TAM is, the RAM is getting close. We always like to, and thanks for your question, Samantha. We're on the final stages of the TAM 1.8 development, and we're trying to get a release candidate out in the next several weeks. And once we have a release candidate, we have a period of testing where we don't like to make any more changes, and then it will be available to the market. As with any new product, as I'm sure you're aware, you have to eliminate all the bugs when you do that. We've had pretty good success running it on wells. That one I showed you that was on an observation well since March has been working flawlessly. Ken and I set that up on the well in the first week in March, and we haven't been back to that well since then. And it's in a real remote area. It would take us about a 2-hour plane flight and then a 2-hour drive to get to that well. So we feel it's pretty stable right now, but it's in the near future. But we're in the final stage of the testing. It's hard to say until we finish all the testing on it. But we have a handful of customers here domestically in the U.S. that are using it.
One last question on the static borehole pressure on the gas lift well. We have said to perform a static borehole pressure on the gas lift well, you would have to bleed off all of the casing pressure before you start, right?
I don't see the need to bleed off the casing pressure. I think it might even be beneficial to leave it on there, especially if there's no packer in there, because if you bleed off the casing pressure, then you're affecting what's going on at the formation and the inflow and bringing liquids in the backside. If you have a packer in there, it probably doesn't matter. You should have check valves in all your valves. You shouldn't flow back into the annulus, but off the top of my head, I don't see a benefit of doing that. Somebody else might chime in on that. I would tend to leave the pressure on the backside on the annulus.
Yeah, I don't see a reason why you want to bleed off the pressure. Founder's asking, in those cases where a very low API, let's say 7 to 8 API degrees, does the sulfur follow the same criteria to calculate the starting borehole pressure?
Juaner, that's a really good question, because an API of 10 is about what our typical produced water is. So what you're really asking is, what if the oil's heavier than the water, where the oil's going to be on the bottom? And we addressed some of those issues when PAM was first developed, and I don't recall that. I remember Tony bringing up those questions 10 years ago when we were working on PAM. When we bring in the pressure transient, it's going to give us an opportunity to refine the static bottom hole pressure calculations, and we are going to go back and look at them. I just have to go back and confirm what's going on and to make sure we addressed it properly. I remember that we discussed it, but off the top of my head, I can't guarantee that we implemented correctly. And if it wasn't implemented correctly, we will go back and revise it when we start working on the pressure transient.
I don't think we have any other question. Any extra comment, Dr. Podio, Dieter? Anyone, Carrie-Ann?
Thanks to everybody for participating. And thanks for Tony and Gustavo for helping put this presentation together, and Carrie-Ann for organizing it all.
Thank you, Dieter and Gustavo. It was a great session. And of course, we'd like to thank all of you for joining us today and for your questions. If you do have any follow-up questions, we always welcome your calls and emails. So we appreciate your time today. We're so glad you joined us, and we look forward to seeing you all again next Wednesday. So have a great week.
Thank you all.
Thank you.
Thank you.
Thank you.